Welcome to another lecture for 2DM3. So maybe let's talk a little bit until the rest of the class shows up. It seems we're missing a lot of students. So just want to point out some stuff that's happening for the next midterm. You've had syntax checking before, where you can make sure everything was well formed. Now you get proof checking, okay? So the system will tell you whether your proof is right or not during the test, like homework or exercise, time crunch, okay? So the point of adding proof checking is you really should know how syntax works by now. There's no need to, test you on that. And we're moving on to chapter 4, right? Relaxed proof style. And hopefully today I'll get to for any syntax. And if you don't know chapter 4 or the for any syntax, proof checking won't make a big difference. It really won't matter if you have proof checking or not if you're not comfortable doing the relaxed proof style. So the upcoming midterm is definitely on the relaxed proof style of chapter 4, LADM, as well as the for any syntax that I'll introduce today as part of quantification, okay? The midterm has been written. It's not clear if we're gonna leave the loop questions in there or not, because it might be a bit long. If we take the loop questions out, then we might have to put in specific questions on quantification, because the two are very related. And a homework prep for the midterm will be posted hopefully later today, which again, it has been written, but we need to decide what's actually going to be there. The prep will be, I think the prep might be a bit long. It took me around 4 hours to write. So yeah, it took me about 4 hours to write. I wrote it this morning, so it might be a bit long because it might take you maybe twice as long to actually solve it. But I wrote it specifically to help you with the midterm. So here's hoping. I hope it's not longer than the assignment. If it is, I'm sorry. I don't think it's that long. I don't think it's as long as the assignment, because I really quickly wrote it up this morning. Okay, 4 hours might be not that quick, but why is it that long? I got excited, but really I wanted to give you guys more opportunities to practice the proof style of chapter 4, and the homework prep is geared towards getting you to practice the for any syntax. So a lot of the stuff isn't new per se. So I reference assignment 2 a lot in the new one. So I'm like, hey, remember from assignment 2, remember from assignment 2, remember from assignment 2. So I reference assignment 2 a lot on order theory. So it's really helpful if you have assignment 2 done in advance. But the idea is it's just more problems to get you ready. Some of the problems in the midterm prep, some of the concepts might show up in the midterm. Hint, hint, wink, wink, maybe not. So yeah, so that's why it might be long. I tried to put in some stuff that you might see in the midterm. Yeah, can we use the theorem list for the midterm? Yeah, we'll probably put a link in there. I forgot to put a link to it. Yeah, that might be a useful thing to put a link in there. I tried to give you the theorems you actually will need. I tried to be like, hey, remember you have access to this kind of stuff, to try to make it accessible. So hopefully that's enough on the midterm. So I'm not going to post which exercises and which homeworks, because I wrote the midterm prep. The midterm prep is to cover the stuff you need to know for the midterm. So that was the point of writing a midterm prep. So before, we just told you, know all of these notebooks and exercises. And now I'm like, know at least the midterm prep. The midterm prep is something you should at least be able to do. So I guess that's why it's kind of long. It's instead of giving you a lot of notebooks to look at, I just gave you this one midterm prep homework to look into. How many notebooks is the midterm? I haven't split it up. Maybe I'll make it 2. I just wrote one big notebook right now, but it might be 2. I'm not quite sure yet. It might be split up into 2, just so that way it doesn't look intimidating. All right. Okay. I'm glad that some of you think it's a good way to midterm, to actually give you a midterm prep, right? So that way you can try doing that, and if you're like, oh, I'm not comfortable doing some of these things, then you'll know right away. Okay. All right. So I hope that works out. If you find the midterm prep to be too long or too difficult, then in the future I won't bother making a midterm prep. I'll just be like, hey, look at all these notebooks and stuff. Alrighty. So are there any other questions, concerns, queries before we begin? So last time we had Isra volunteer to be the person who says words to make sure I haven't disconnected. Does anybody else want to take on that role today and say words occasionally? Like, yeah, algebraic, mathematical, trigonometric. Does anybody want to volunteer to do that?
Mathematical.
All right, Dipinder Singh will occasionally say words. When I ask a question and no one replies, I expect Dipinder to say words. The midterm prep will probably be assigned as a homework. Yes, that's the plan. So details aren't fully hashed out. Some things are still not fully complete. So, but it will probably be a homework to help you get ready. Anyhow, so let's begin. All good? Any questions? Dipinder, this is your time to shine.
No, sir.
Mathematical indeed. All right. So we talked about quantifiers last time, right? The idea is that quantifiers implement loops, as it were. We in particular said that whenever you have a ... notation, right, this informal ... then what you're doing is that the ... is informal for the formal notion of a quantifier. Okay, and we said you can have them for sums, products. You can also have them for essentially any arbitrary commutative monoid, which you are all comfortable with from assignment 1. Okay. Then we talked about how the rules for quantifiers can be thought of as rules for loops, right? The empty range rule says, you know what, if the loop never runs, then you essentially have only the initial assignment, right, for the running total. Okay. So yes, Stanley, there may not be any homework besides the midterm prep, because the midterm prep might be long. Okay. So that's what loops covered, right? We talked about these ideas of these distributivity theorems or range split, right, as a form of optimization laws. Okay. All right. Great. So today we're going to talk about this upside down A and upside down E, known as exists and for all. Okay. So let me just make some stuff down here. Boop, 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 boop. Okay. So exists is just entered with like that, and for all is just for all. Okay. And they use the same syntax as the other quantifiers. Okay, ducks. Let me go to an actual text block, so that way this doesn't get checked. All right. So let's consider this one, for example, over here, right? For all k of type natural number, we have that 2 times k is at least k. All right. That's a bit awkward to read. What we're saying is for every natural k, twice k is at least k. Okay. What we're saying is the double of a number is at least the number. Okay. So you can read these very rigidly as for all k of type natural, we have that 2 times k is at least k. Or you can read it more colloquially as the twice of a natural number is at least the natural number. Okay. Right. Or if you like, the twice function is ascending. All right. not ascending. A continuous an closure operator. All right. Okay. All right. Good. All right. So let's just quickly go back to some of the stuff we might have not covered. So this one is really important. It comes up quite often in some of the more difficult cases, and you probably saw it sometimes in assignment 2. So you'll probably see it a little bit in the midterm prep as well. You might need it for the midterm, for example. So let's cover that. All right. So we've talked about with before. Just a quick reminder about that. All right. When you say with, you're just applying, it's essentially like function application, right? I have a theorem that says, given a premise, you can get a conclusion. And I have a premise for a particular choice for something called x0 or x0. And so when I say T with G, I have the conclusion, okay? So that's all it is, right? So we can try, I won't spend some time on it since we've used it already. I'll just quickly go over the slides, and if you want me to stop and actually show you some stuff, please let me know in the chat. But since we've already talked about this, I won't spend too much time on it. I'll try to get to some of the newer stuff today. So just a bit of review. Okay. And as always, you have access to these slides on Avenue. Okay. Okay, dokes. So contrapositive, right? If you remember, just lets you flip things around, right? And as always, sorry about that, we can use the keyword using to let us use a theorem as if it was a proof technique, okay? So let's prove a really simple theorem in comparison to this one right here. Let's prove a simpler one. Let's say theorem, if I have not P, and I have, I don't have a good theorem off the top of my head. So we'll just walk over this little one right here. Not a big deal. So we're using contraposition, right? To say, you know what, we're going to prove this theorem by looking at its negation. We don't want to prove that a plus gives us an or. That's not that easy. How do you get an or? But if you have an and, right, which is the case down here, then from an and we can simplify to getting a single inclusion, right, or its negation. Right. Okay. All right. All right. So the main one I want to talk to you about today is mutual implication. Right. So if you did the homework, you will have seen this form. You will have seen this form where you say x is less than or equal to y, and y is less than or equal to x equivales x equals y, right? So it's not a property specifically of implication. You can also use it for any order. Okay, so another keyword, order, from assignment 2. So a word you might want to know. So implication orders the Booleans, as we said before. You have true and you have false, and false is less than or equal to true. False, true. Okay, and we're saying if P is contained in Q and Q is contained in P, then they must be the same. Okay, so this is the mutual inclusion theorem. Okay, and you can use it, for example, here, but you can also use it for other ones. All right. So let's prove a theorem maybe together. Theorem. Let's prove mutual implication. It's using the technique. Okay, so not a fancy theorem, but so P implies Q, and Q implies P equivales P equals Q. All right. So if we want to prove this theorem itself using mutual implication, man, I got to come up with more interesting theorems, maybe. All right, let's come up with a more interesting theorem. Let's see. Can we do P land Q equivales P equivales P implies Q? Okay. So let's try proving this theorem using mutual implication. It is the definition of implication, but let's pretend we didn't have that. How does that sound? All right, then we can, sure. Let's just try it. Proof using mutual, using mutual implication. I have a subproof for P let Q. So this one implies P equals P implies Q. Okay. And we have a subproof for the other way. For P equals P implies Q implies land Q. Okay. So to show this equivalence, we're just going to show that the left-hand side over here is equivalent to the right-hand side over there, right? And we show that by saying one of them is included in the other. Okay. So it's not a very interesting theorem, but I just wanted to show you the idea. You should have seen it, of course, already in assignment 2, but a bit of a reminder hopefully will help. So, but we'll do it using chapter 4. So we'll assume, let's call this A, we'll assume P and Q, okay? And now we'll show, so we'll start off with P, okay? Equals, and we want to end up with P implies Q, okay? Okie dokes. So how do we do that? Who knows what we should try first? All right, so let's try to be interactive like last time. What should we try? Okay. Weakening. How do we try weakening? What are we doing with weakening? Another person also says weakening. So what are we trying to do with weakening? Golden rule. Sure, let's try golden rule. We have a conjunction, and we have one part of the conjunction, and we're not sure what to do. And we don't know how to exploit this conjunction. Using the golden rule is very easy. Okay. Okay. So we can try the golden rule. There are other things we could do. We could introduce an identity and then manipulate from there. So let's just try the golden rule and see where that takes us. All right. So this is going to be P and Q equivales P equivales P or Q. Okay. Then what do we do next? Okay. All right. Okay. Can everyone's good? Everyone's fine? All good? Is some people seem to be having problems? Technical difficulties? Good? All right. Okay. Great. Okay. Thank you for confirming. Thank you. All right. All right. So what do we do next? What do we do here? So I'm just giving it a name. So this is what I'm assuming. All right. This is an implication. So I assume P and Q, and now I need to just show this part. And I'm just going to name it A, because A is a nice name. I can name it something else. Nito Petito. Okay, so I can name it another name. All right. So what should we do here at the holes? Does anyone know what we should do? So it seems, so this is the good thing about showing live calculations. People suddenly have more questions. So we're showing, all right, and using mutual implication says we show the left side, so right here, implies the right side. Okay, so this part gives us this part. And so that's what we're trying to do. We're saying start here and then go all the way over there. Then start on the other side and try to get the left side. Okay, so we're doing mutual implication. Okay, mutual inclusion. Okay. Does that help, Tammy? Okay. All right, excellent. Shrill, we started the proof with a golden rule because somebody blurted it out. That's all. There are multiple ways to start the proofs. We could have started at P implies Q. We could have taken the whole thing and shown it equal to true. Somebody just suggested it. Thank you for identifying yourself. All right. So what do we do here? Does anybody know what we do here? So I'll do the last one. We'll get rid of that one. Definition of implication. But what's this hole? What do we do in this hole? All right. Well, this hole is interesting. What do we do in the hole? Jeez. Yes, exactly. So we use our assumption. Assumption, and what's our assumption called? It's called nito petito. Okay, right. You can just name your assumption if you want. You don't have to. I think it's a good idea to give them a name. And of course, we're also using the identity of equivalence. We're doing two steps in one go. Ready? Okay. And now the second side. All right. Does anybody want to see the second side done real quickly, or should we just do it again, just for practice? Let's do it again, actually. So we're assuming that thing, okay, which happens to be P equivales P implies Q. So that's what we're assuming. Then we want to show P and Q is true. So P and Q equals this. So what should we do? All right. So assuming just lets you take an implication. So we have this implication right here, and we're saying, hey, let me just pretend this is an axiom. That's what assuming does. And now let me just try to show this part is true. So this thing is gone now, and now I'm just trying to show this thing is true. Okay. Definition of implication into assumption. All right, so somebody says, let's try using our assumption, which happens to be that thing. Okay, and it says you have P implies Q and Q. Okay, now what should we do? So somebody's asking about this step now. So nito petito says P and Q is true. So this part is true, all right, TRU. And then identity of equivalence removes that part. Okay. All right. Alrighty. Excellent. Assuming is only for implications. Okay, so this is stuff you need to prepare for the midterm. Okay, you definitely need to know assuming for the midterm. Okay, all the best. Excellent. I'm glad you're asking questions. I feel like I'm silly sometimes, showing you stuff and making mistakes, but you ask questions, so that's good. All right, so what should we try doing here? So people are still talking about this one, so let's go back here. We're showing this equivalence by showing the left-hand side implies the right, and conversely, so they're mutually included. That's what the theorem mutual implication says. If two things are mutually included, then you have P equivales Q. All right. So we're going to start with the left-hand side and try to get the right. This is the left-hand side, and we want to get to the right. So assuming lets us get rid of this implication. This implication's gone if we use the word assuming. Now we're going to try to prove this. we started with P because somebody suggested let's just start there and do golden rule. We could have taken the whole thing and turned it to true. Okay? Yeah. Alrighty? Okay, good. So right here on the side I have equals, because if you recall, equivales on the Booleans is just equals. So you can have equals right here or equivales. Either's fine when you're talking about Booleans. Okay? All right, excellent. All right, great. I'm glad you're all learning and asking questions. That's the purpose of this. No, don't worry. That's fine. You're asking questions and you're learning. That's good. All right. I believe assumption and assuming was already on some of the exercises, and it's definitely going to be on the homework prep, and it will definitely be on the midterm. So this syntax is definitely something you need to know how to do on the midterm. This is definitely a part of the midterm. All right. We give you proof checking. We give you the green stuff over here, because if you can't use this syntax, then the proofs are really hard. The proofs will take a long time if you don't use the relaxed proof style. Okay, so that's why we're giving you proof checking to help you out. But you really need to be using the relaxed proof style. Okay. This is a double quote, like normal theorem names. This is a double quote, and these guys are backticks. Okay. Yeah, exactly. Okay, good job. Excellent. So the only time to tell when to use the relaxed proof style is to do a lot of the problems. So that's why we're giving you a lot of notebooks, and that's another reason why the midterm prep is so long. It's to give you chances to practice doing it. Assignment 2, which you received a while ago, used assuming, and assignment 2 mentioned when you should be using the relaxed proof style. Highly recommend you have assignment done or nearly done before the midterm. The assignment 2 is something, we gave you extra time to work on it because we didn't want to rush you, and you had reading week. But assignment 2 really is integral for the midterm. So definitely please do assignment 2 if you haven't already. And you kind of want to have assignment 2 done before you even do the midterm prep. We give assignment 2 till next week for you to have it completed, but you should at least be comfortable with some of the content in assignment 2. Okay. All right. So assumption that thing, how did it work? Well, it says P is equal to P implies Q. So here's a P, and we replaced it with P implies Q. Okay. The relaxed proof style just makes it easier to do proofs. You can use the regular proof style all you want, but some of these theorems will become really, really long if you try to do the classical proof style. They'll just be really long. Like this proof is like, I don't know, 15 lines. If you do the traditional, the lines will get really long. Because if you look right here, an equivalence is expressed as a pair of conjunctions. So you see how there's a subproof and then another subproof? If you don't use this style, that means you're going to have, on each line, you're going to have this part and the second part down here. So your lines are going to be this long and then an additional this long. So your lines are going to be really, really long. And it's going to be really hard to keep all of that in your head. Okay, dokes? I'm thinking of giving you guys 2 hints on the midterm, 2 hints per step. Okay. So who knows how do we wrap this up? What can we do here really quickly? So we can do definition of implication, and then what? Does anyone know? Or what should we do? We could do replacement. Maybe I'll do a replacement so people get practice. So let's do substitution. P implies Q, and Q. So here, let's call this one W, and here we'll say with W becomes Q. And let's also do identity of true, so that this is equal to true. Okay. All right. So somebody's asking, what does it mean when I say using mutual implication? It means I'm going to prove the result by first proving one implication, then proving another implication. So that's what the theorem says. Right? Mutual implication says to prove an equivalence, first you prove one side implies the other, then you prove one side, the other side implies the other. Okay? So sometimes this is called a ping pong proof. You ping, then you pong. Okay? Excellent. No, don't worry. This is why you're asking questions. You're learning. This is completely fine. I'm glad you're asking. All right? Yeah, I want you to learn. I want you to do well. So I'm glad you're asking. Don't worry about it. Aaron, you can use the keyword is using. Okay, so here, calc check. Here, this one. Here, if you go to documentation, I've tried to put some for you, but using is the one that lets you use any other theorem you want. Okay, so the key phrase here is using. All right, it lets you prove some stuff. Okay, so using is what lets you use a theorem as a proof technique. So using is the keyword. Okay, mutual implication just happens to be a theorem that we are using. Okay, exactly, yeah. You can use other using theorems if you want. Mutual implication is just it's a very useful one. That's why we're mentioning a mutual implication, contrapositive, proof by contradiction. These are just very useful ones to have. So we're just paying specific attention to these. There are other ones. I don't have any right here. This one right here, for example, uses indirect equality from below. Okay. So look, so somebody was asking earlier, here's a classical proof. Notice it's kind of long, right? I have to like scroll to show it to you. Here's a relaxed proof style, and it just has more indentation. Okay. All right. Yeah, you can use any relaxed proof style whenever you want, going forward. Okay, anyhow, so everyone follows down here what we're doing with substitution. So now we can do definition of equivalence, right? Which turns it into an equality. Right? P implies W with W slash becomes Q and Q equals true. Okay, exactly. And now the next step is replacement. All right, so we'll just do them both together. And replacement. Okay, so if I do replacement, this becomes true. Okay, becomes slash colon equals. Okay, so slash colon equals. Slash colon equals. Okay, that's how you make that one. And then we can wrap up, of course, with substitution and definition of equivalence to get P implies TRU true and where are we? And Q prevails true. Okay. All right, excellent. All right, so I'm just gonna stop this one and we'll move on to other stuff. I feel like we're just beating the horse right now. Okay, sound good? All right. All right, so of course we can also do contrapositive. So as I've said before, I'm just leaving all the 3 slides here since we're doing a lot of a demonstration. So that way you can look at them as you see fit. Can I go back? Yeah, I can go back to the previous slide. Here you wanted to see something? Oh. Okay. So all right, we can discuss that in afterwards if you like. So that's no problem. So and of course there is, yeah, and so of course there is the proof by contradiction. To show something is not true, show that it implies false. Okay. So existence and quantification and the universal quantification are discussed in chapter 9 of the book. And the idea is they represent the same kind of things as before, right? So when we say for all x with, for example, 0 less than or equal to x less than or equal to 3, and then here I have p of x. What this means is just p of 0 and p of 1 and p of 2 and p of 3. Okay? Sorry about that. Okay. And likewise, when we do existence, right? Instead of ands now, however, we're doing ors. Okay. So there is very little new content here. It's just quantifiers, but now we're talking about the booleans. Okay. All right. Okay, great. All right. Excellent. Okay, so there's not that much new here, right? Here's a few phrases on how to talk about them, but let's talk about the syntax for how to use these things. So let's do a calculation. Suppose I have for all x slash with, and I know that I know some property about x. For example, I know x is less than or equal to x. Okay. Suppose I have this property. Okay. Let's use less than actually. Okay. Then I can show that, for instance, x is less than or equal to x is true with x becomes 4. Right. So if you remember way back when in chapter 1, we talked about substitution, which said when things are true, which said when things are known to be true, sorry, when you know a formula is true, then you can substitute values for it. So here we know that x is less than or equal to x, and we can substitute a choice for it. This is known as instantiation. And I did not enable instantiation apparently. Axiom instantiation. How do you spell this word? Instantiation. Whenever you have for all x p, then you can say p with x becomes p. Okay? So we can also apply instantiation to get this. All right. Yes. Okay. Oh, did I spell instantiation wrong? I did not have it loaded in apparently. Okay. So here's instantiation. Found could not justify. Ooh. Sorry, I had a typo over there. Okay, so we can apply instantiation. Then we can of course use substitution as usual to get 4 is less than or equal to 4. Okay. So I just wanted to show you how to actually use these things. Sorry. Equals silly little mistakes you make when you type real fast. All right. So whenever you have a for all, this is just saying all of these things are true. But if they're always true, okay, then that means they're true when I pick x to be 4, right? So instantiation is really, this is a form of weakening, okay? So you remember if you have P and Q, then you have P, but a for all could not resolve theorem reference. It's just not the right thing today. Okay. So then, when you have a for all, it's true for all possible values, and so this is like weakening. I picked the possible value 4. Okay. So that's a theorem that you will need to know for the midterm. Okay, so I just wanted to bring that one up. But many of the familiar laws about and or generalize to for all and exists because they're just repeated forms of them. So let's, and as I said earlier, it's the same syntax, so nothing new here. We've already talked about how you can use the syntax for arbitrary commutative monoids, right? So you can use it for any one of these guys, okay? So, and as we mentioned before, the book will use small operators. We're going to use the big forms, right? So right here, I mentioned some big forms last time, right? Plus is sigma, times is pi, and is for all, and or is exists, okay? All right. So they have the same kind of rules as before. The unit of and, what's the unit of and? It's true. So empty range will give us true. The unit of or is false. So we get false for the empty range. The unit of plus is 0, right? So this is this rule right here. Okay, so there's not much, just, you know, the same rules you saw before, but now for all it exists. Okay, so that's why I didn't spend too much time on them. Again, the same 1-point rule, split off terms, right? So we talked about bound and free variables last time, right? So I'm not going to spend too much time on it, but what we didn't get to last time was this occurs meta predicate. So sometimes CalcCheck will let you know, hey, this variable should not occur here, and it will mention it using this occurs meta predicate, which is also discussed in the book. It's just to let you know you have a free variable where you shouldn't, right? Or there shouldn't be a free variable in a particular place, right? So somebody was asking about this. Okay. So we talked about some instances of the 1-point rule failing before, but before we talked about sums and products. Now it's a similar setup, but now involving for all and exists. So the same knowledge you knew about sigmas and products, right? Everything you knew about these guys now applies equally well to these guys, okay? So here's a new one that we didn't cover last time. When you want to substitute inside a quantifier, right, you need to make sure that the dummy variable y is not the same as x or f. Otherwise, you might be introducing new things. Because remember, a quantification like a for loop doesn't really depend on the dummy variable, right? It doesn't really depend on y. So if your expression adds extra dependence, then these guys are different, because I can change y here and it will change all occurrences. But if I change y here, it won't touch the occurrences outside. Okay, so it's again scope. All right. And we talked about meta variables before, and they're also on the CalcCheck reference. So I'm just not going to go over them again. All right. So somebody is asking about the units. So the identity of or is false, right? The identity of plus is 0, okay? And so when you have exists x with false spot p, right? This is just or x with false spot p, which is just the unit or the identity of or. So this is just false, okay? And then you can copy the same thing to the next line, and we can say, if I do a sum over some expression p, this is a plus, and this is now 0. Okay, so the empty range just talks about the identities. Okay, ducks. So I'm just going fast over these things that we've already covered. I just want to show you an interesting one. So then the main new thing, besides the, so we talked about dummy renaming last time on how the name doesn't really matter, you can change it, right? And that's why in this one, you have this proviso. Otherwise, if you change the dummy here, the change won't be reflected over there. They'll have extra changes in F, for instance. So here's a new one, De Morgan. We said all properties of and or kind of generalize to the quantification case because the for all is just iterated and existence is really just iterated ors. And so De Morgan says when you negate an and, you get an or, and when you negate an or, you get an and. So likewise, when you negate an existence, you get a for all. Okay, so we refer to this as generalized De Morgan, and we'll prove it in time. For now, I just wanted to mention it. Okay, and the proof actually follows very easily from this particular form, right, which we take as an axiom. Right. So I just want to wrap up real quickly, and then I want to get to some more examples. So just some forms for all x, right? That's the same thing. So we're considering the x that have property r, and then we're going to do an iteration. So we're going to consider all these p's, but we don't want to consider just any x. We want x to be between 0 and 3, right? So we can move them in as an implication, right? But then if you move them in as an implication, you know an implication is the same as a negation with a disjunction. It's the same thing as an and an equivalence. It's the same as an or and an equivalence, okay? And then if you have Q and R, you can, of course, do trading, and then you can do shunting, and then trading back. So all of these forms follow from the main one, trading, okay? So this is a new property that the old quantifiers didn't have. But we can add it to the old quantifiers as well. For all and exist are in chapter 9. Okay. So let's try doing an example, because I feel like we talked a lot and we haven't really done an example yet. Let's prove a theorem. For all x for all x with x is equal to 0, we have that 0 is less than or equal to x. It's a very silly little theorem, but the idea is just to show you how it works. So we're going to show for any x satisfying x equals 0, right? We'll try to prove a theorem. Okay. So what theorem are we trying to prove? We're trying to show that 0 is less than or equal to x. Okay, well, we can use our assumption that x is equal to 0 to get 0 is less than or equal to 0. Okay. Okay. And then we can just do reflexivity of less than. Okay. So it's a silly theorem, but the idea is just to show you how you can prove a for all this way, right? Of course, we can also prove a for all more directly in the classical way. Right? So here is where we are. For all x with x equals 0, spot 0 is less than or equal to x. We can apply trading to get for all x with spot x equals 0. We can also, of course, use 1-point rule, but I just want to show you how the similarity would work here. 0 is less than or equal to x. Then we would need to apply substitution and replacement, right? To get to x equals 0 implies 0 is less than or equal to 0. Then we need to apply 0 implies. Then we need to apply the reflexivity, and then finally we can apply for all x slash spot. This is true, and then this is a vacuous true, and then we can get to true. So if it wasn't a 1-point rule, in general, not using the relaxed proof style could result in rather long proofs. And notice how we used a satisfying clause to make the assumption on x, the constraint or the range constraint, to hide it away, as it were, to make the calculation focused on the body. Here we had to hold everything in our head throughout. All right. So as somebody says, you don't have to write for any. If you want to prove it, you could just prove it directly using a standard calculation. You don't have to use the for any syntax. Okay. What theorems do you use to get from for all x true to true? I think we called it the vacuous true theorem. Let's see if I have it activated in my notebook. I don't have it activated in my notebook right now, but I think we called it vacuous true. I'll have to look it up in the CalCheck reference. All right. So our time has run up. So I will cover. We've already talked about monotonicity, and we'll get back to it, I guess. We've already talked about using instantiation, but I'll bring these up again for next time. So don't worry. I'll bring them again for tomorrow. All right. So don't worry if you're feeling not comfortable. We'll talk about them again tomorrow. I just wanted to show you some stuff at the end. And yeah, for those of you who have to go, and we should close, have a wonderful day. And yeah, I hope you enjoyed this lecture, and hopefully things will make more sense as we keep going on. And please practice. Do all the homework that we're writing for you, all right?